This is Algebra 1, Lesson 7-1. In today's lesson, I expect you to be able to simplify the multiplication when you have similar bases, or the same base, I should say. So first, I want to talk about the product rule. Essentially, I want to multiply this x to the power of 3 and x to the power of 2. The thing that I want to point out here is these are the bases. These are the numbers that are in the bottom. These are the powers. The bases are the same. I have x and x. So if I have any other bases that are the same, say 2 and 2, that still applies. So how do I think of x to the power of 3? Really, x to the power of 3 is x times x times x. How do I think of x to the power of 2? It's x times x. When I multiply these all together, I can say this is x to the power of 1, 2, 3, 4, 5, and this is really x to the power of 5. So really here, the shortcut here is I'm supposed to do x to the power of 3 plus 2 in the exponent. This power up here, you'll always be adding whenever the bases are being multiplied. So to simplify the rule, the one that you'll typically see in the textbook is if I have any two powers up here with the same base down here and I'm multiplying those bases, it will be just one of those bases, and I have a plus b. A very common mistake is to think, oh, I have to multiply the x and the x. So for example, if I have like a 2 to the power of 1 times 2 to the power of 1, I have to do 2 times 2, which is 4. It's going to be 4 to the power of 1 plus 1 is 2. You do not multiply the base. You keep the same base. This base does not change at all. All right, so there's a few other things that I need to go over before we can get into our example problems. First, I need to talk about the powers of 0. Anything to the power of 0 is, did you say 0? Because it's actually 1. Anything to the power of 0 is 1. And because x means anything, x to the power of 0 is also 1. This is the rule most often seen in textbooks. So my question here is why? Why is anything to the power of 0 1? And the general answer is because it works and it's consistent. Check out this pattern. I have 2 to the power of 3, to the power of 2, to the power of 1, to the power of 0, and I'm going to look for patterns over here. 2 to the power of 3 is 8, 2 to the power of 2 is 4, 2 to the power of 1 is 2, and notice what's happening. 8 to 4, I divide by 2. 4 to 2, I divide by 2. I'm going to keep this pattern going, and I'm going to keep on dividing by 2. If I divide by 2 yet again to get from here to here, 2 divided by 2 is 1. Therefore, it completes the pattern. And in fact, this I could have chosen a 2, I could have chosen a 3, I could have chosen any number here. This will always be 1. So any number to the power of 0 is 1. I think I've explained that with the pattern. And there's another rule that we need to talk about. Anytime I have any base to a power of a negative, I chose negative a here, although it looks like a negative 9. I'm going to rewrite that as a negative a. Anytime I have a negative power, I flip it and make it a positive power. This used to be x over 1. So I'm going to flip this. This is now going to be 1 over that x. And now instead of having a negative a, I'm going to have a positive a. Again, this is one of those questions of, this seems weird, Mr. Snell. Why does this happen? Why do I flip it? And again, it comes from this general pattern. If I continue the pattern down where I go from powers of 3, 2, 1, 0, and then I keep going to negative 1, I keep this pattern going and I keep dividing by 2. If I divide by 2 to get from 1 to this number down here, 1 divided by 2 is 1 divided by 2. And if I keep the pattern going again, and I keep dividing by 2 to get from here to here, 1 divided by 2 is a half. If I have a half and I divide by 2, that's going to be a keep it, change it, flip it, and that's going to be 1 over 4 because I multiplied the numerator, I get 1, I multiplied the denominator and get 4. And I can keep doing this pattern. When I divide by 2 again, this 4 is going to turn into an 8, 1 over 8. And you can see if I write this out, this is 1 over 2 to the power of 3. And that 3 is a little bit thick, but I can make it a little bit easier to see. Notice what I had. I had 2 to the power of negative 3, and I flipped it and made it 1 over 2 to the positive 3. Again, right here, I had the same thing. This is 1 over 2 to the power of positive 2. This is 1 over 2 to the power of positive 1. All I do is when I have a negative power, I flip it. I make the 2 on the bottom, the denominator, instead of the numerator. And instead of having a negative exponent, I have a positive exponent. All right, let's try some example problems. So I have the same base in all these problems. Whenever I have the same base, I'm going to add the powers. One unspoken rule of all my simplification in my class is anytime that you have a negative power, go ahead and flip it to the other side and make it positive. So when I don't have any power, you assume that that power is 1. All right, now I'm ready to do this. This is the same thing as v to the power of 2 plus 1 plus 3, which is v to the power of 2 plus 1 is 3, 3 plus 3 is 6. This is v to the power of 6. In example 1b, Again, I have the same base, so I'm going to keep the same base. I do not change it, and I'm going to add 3 plus 6 plus negative 1. 3 plus 6 is 9. 9 minus the 1 is 8, so this is 2 to the power of 8, and I'm going to leave it in that form, although I could expand out 2 to the power of 8. What would that be, like 256 or something like that? Let's move on to example 1, part C. Now I have coefficients out front. There isn't any additional trick for coefficients. Everything here is being multiplied. Really what's happening here is I have a multiplication symbol there, and there, and there, but they were hidden, right? So the first thing that I'm going to do is deal with the multiplication of the coefficients. 2 times 5 is 10. 10 times 4 is 40, so the coefficients are going to multiply to 40. Notice the rest that's left over have the same base. This is an A. And then because these are all A's and there's multiplication happening, there's only going to be multiplication happening in all of today's lesson, I'm going to add the exponents. 3 plus 4 plus 0. 3 plus 4 plus 0, which is kind of silly. You don't ever need to say plus 0, which is the equivalent of saying, hey, anything to the power of 0, I can cross that off. Here, I'll even do it in a different color. I'll cross that off because it's really 1. I know my rule that any power of 0 turns into 1, so this A turns into 1. A very common mistake here is thinking that if I have a power of 0 here, this entire thing is 1. Do not make this mistake. It's only the A that crosses off. You do not cross off the 4 and the A, just the A turns into a 1. I still have the 4 left over. When I simplify this, this is 3 plus 4 is 7. There's nothing there, so it's still 7. My final answer here is going to be 40A to the power of 7. All right, moving on to example 2, A and B. These are slightly harder problems which relate to the problems in the homework that are later. Again, I'm looking at the coefficients. I see a 3 and a negative 6 that are being multiplied. 3 times 6 is 18. A negative times a positive is a negative, so this is going to be a negative 18. Now let's look at all the x's. Again, really there's a hidden multiplication symbol happening between every single one of these terms. So everything is being multiplied. I have an x and another x. I don't have any power here. When you have no power, you assume that power is 1. So really I have x to the power of 1 times x to the power of 2. Because I'm multiplying, I'm going to add the exponents. 1 plus 2 is a 3. This is x to the power of 3. And then I'm going to deal with the y's next. Y is 4, y is negative 6. If I add a 4 and a negative 6, I'm left with a negative 2. Remember, one of the unspoken rules in my class is when I simplify, I never want negative powers. So even though this is mathematically correct, I prefer it in the form where every single power is positive. The way that I do that is technically, this is all over 1. I'm going to flip this y down to the denominator, and instead of having a negative 2, I will have a positive 2. So my additional step here will be to put just the y, just the base that had the negative exponent. These had positive exponents, technically a positive 1 and a positive 3. So these are going to stay behind. I have a negative 18 and an x to the power of 3 that are staying in the numerator. The denominator is now a y to the power of a positive 2, and here is my final answer. Our last example for our notes is B, which looks like a monster. Look at this thing. I have a bunch of multiplication happening. Multiply, 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 multiply. Everything is being multiplied. First, I'm going to deal with the coefficients, 7, 2, and 3. Well, 2 times 3 are smaller, so I'm going to start with there. 2 times 3 is 6, and 6 times 7 is 42. So my coefficient out front is going to be 42. Let's deal with the A's next. So when I deal with my A's, I have a power of 4. I'm going to write this down, power of 4, and I'm going to add a power of 0, which is silly to say. I mean, power of 0, that just goes to 1, so I can kind of ignore it, because 2 times 1 is just 2. And then I have an a to the power of 2, so I'm going to say plus 2 up here. Oop, I want to do that in blue, though. Plus 2, and I'm done with my a's. Let's go ahead and analyze all the b's. I'm just going to put it right here. I don't need to write the multiplication symbol. If I just squish things, you assume that they're being multiplied. If I have a power b, I have a b there, nothing there, nothing. Okay, I literally only have a b to the power of 8, so I'm just going to rewrite b to the power of 8. And finally, let's analyze the c's. I have a c to the power of negative 1, so I'm going to write down c to the power of negative 1. I have no c's right there, and I have a c to the power of negative 3. So I'm going to add this negative 1 with the negative 3. Again, I'm adding because I'm multiplying the bases. So I'm going to add the negative 3. If I simplify this, this is going to turn into a 42, a to the power of 6, b to the power of 8, and c to the power of negative 1 plus negative 3 is negative 4. Again, that is mathematically correct, but it's not in the form that I typically like. I generally will say all powers should be positive, so this c to the negative 4 is going to come down to the denominator, and that negative 4 will become a positive 4. So this final answer here will be 42, a to the power of 6, That's a bad 6. I'll rewrite it. A to the power of 6, b to the power of 8, all divided by c, not to the negative 4 anymore, but a positive 4 for my final answer, which I will then box. All right, that concludes lesson 7-1 for properties of exponents, just on the product rule. Thanks for watching.